This is the third and last video in nutrition, and in it we're going to focus on proteins. Unfortunately, we're not going to have the opportunity to talk about vitamins and minerals this semester. There are two nice quotes here that I think relate a lot to nutrition. The first, let food be your medicine and medicine be your food. It's true that lots of people in developed countries eat foods that really promote a lot of different chronic diseases, including cardiovascular and metabolic diseases, things such as heart attack, coronary artery disease, stroke, non-alcoholic fatty liver disease, diabetes, metabolic syndrome. And so you really can choose foods which are very healthy for you and are going to reduce your risks of getting chronic disease. Another quote that I like a lot is, the restaurant is a toxic environment, and this tends to be really true. Places like O'Charlie's, IHOP, Cheesecake Factory, Red Robin, we could go on, they provide you with meals that have way too many calories, in some cases 2 times the number of calories that a person might need through the course of a whole day for one meal. On top of that, there's lots and lots of added sugar, there's saturated fat, there's salt, and so these two quotes really kind of go together. Here you see some very healthy foods, and one of the things about the foods that you see here is they're all good sources of protein. And so now we're going to go ahead and talk about protein. What are proteins? This is review for you. You know they're chemical compounds. They're made up of carbon, hydrogen, and oxygen, just like fats and carbs. But in addition to that, they also contain nitrogen. It turns out that about 16% of dietary protein is nitrogen, and we can use that to help us determine whether or not an individual is in nitrogen balance. The carbon, hydrogen, oxygen, and nitrogen are arranged into amino acids, which are indeed the building blocks of proteins. And you know that amino acids have both carboxyl and amino groups that make them up. And so here we can see just kind of a generalized amino acid. It's not any specific amino acid because here it has this R group. This could be anything from another hydrogen to a methyl group to a ring structure. But here's the carboxyl group, the COOH. Here's the amino group attached to that central carbon. And here's just another look at a generalized amino acid. Again, we know it's not any specific amino acid because here it has the R group. But there's the carboxyl group, and there is the amino group attached to the central carbon. And you have amino acids stored throughout the body. The liver, of course, is receiving blood that's high in nutrients, including amino acids, from the hepatic portal vein. You have amino acids in blood and other body fluids, and you have amino acids in your skeletal muscles. So they are indeed all over the place. Now, you know that once we take amino acids up into the body, we use them to create proteins. And what we have to do is we link the amino acids using peptide bonds. Here you can see that we take the OH from one amino acid in the carboxyl group, a hydrogen from another amino acid in the amino group, and we extract the water and we create that covalent bond, which now we refer to specifically as a peptide bond. And so this is a dehydration synthesis reaction. It is chemical work, and so it does require the input of energy for us to create a dipeptide from 2 individual amino acids. Now, normally, we're going to create something that's much bigger than a dipeptide. We create polypeptides, or we create proteins. Occasionally, we create oligopeptides. But here you can see kind of a schematic of translation. Here is the growing polypeptide chain. Here is the next transfer RNA with the amino acid that is going to be bonded to the polypeptide chain next. Here's where we'll create that peptide bond. Here is the next one that's coming in, being brought in by another transfer RNA, and then we'll create a bond there. And so we continue to do this as we make our polypeptide or our protein bigger and bigger and bigger and bigger. And so again, creating peptide bonds is chemical work, and it does require the hydrolysis of ATP to provide the energy to drive that. And so you need to remember that. Dietary considerations for protein. Well, from the dietary standpoint, we divide amino acids into two different groups. We have 9 essential amino acids, which some nutritionists like to refer to as indispensable. You have to get them in your diet. Now, I don't expect you to memorize these, but if you need to memorize them for another class or perhaps down the road, here's a nice mnemonic to help you do that. Private TM Hill. And so here you can see these are the ones that you have to get in your diet. That's what makes them essential or indispensable. And then you can see that 3 of them are what are known as branched chain amino acids, and muscle protein is made up of a relatively high proportion of those 3 amino acids, making some people think that if they get branched chain amino acids while they're lifting weights, that they'll look bigger and buffer. Well, unfortunately, it doesn't work that way. And then there are 11 that are non-essential, meaning you don't have to get them in your diet. It doesn't mean you don't need them. That's why some nutritionists prefer indispensable and dispensable. It just means that your body can make all of these guys. They're still needed. They're still very important. You can see here that alanine is the most important glucogenic amino acid. That means your liver can use it to make glucose. And so it's one of the things that is used in gluconeogenesis. Here you can see that glutamine is important in trauma and illness because it's an important energy source for the white blood cells, especially the lymphocytes. And so there again, alanine is very important in terms of energy metabolism. And so that is indeed one of the functions of protein. It can provide energy. And you can see that you get about 4 kcals per gram of protein, similar to what you get from carbohydrate and less than half of what you can get from the breakdown of fat or lipid. So these amino acids can, in fact, be broken down and be used for energy. They can run through cellular respiration. At rest, roughly approximately 5% of your energy is coming from the breakdown of protein, as long as you aren't fasting. If you're fasting, then that percentage is going to go up. Now, during exercise, you may use more. The studies that we have done would suggest that during resistance training, there's little increase in the oxidation of amino acids. However, aerobic exercise activates these branched chain amino acid dehydrogenases, and that means we're going to run them through redox reactions and stick them into the Krebs cycle or electron transport. And so they can indeed be oxidized directly to resynthesize ATP. Again, as we already mentioned, the amino acids can provide the substrate for gluconeogenesis, and alanine is the major one that does that. Now, when you're exercising, protein synthesis is actually suppressed. It's inhibited. And so protein synthesis is not going on when you're doing heavy weightlifting workouts. But post-exercise, protein synthesis will increase. And so then those amino acids are going to be used. Again, remember, protein synthesis is translation. That's what's going on. As I mentioned in the previous slide, glutamine is an important fuel, especially for the white blood cells, and in particular the lymphocytes. And another interesting thing that we found is that during prolonged exercise without carbohydrate ingestion, I didn't say that very well, without carbohydrate ingestion during the exercise, protein breakdown may account for 15% of the energy that you need. So again, the longer you exercise, the longer you go without food, the more you break down amino acids in order to get the energy that you need. All right. Another functions of protein include regulation of physiological function. There are indeed many enzymes that are involved in energy metabolism and other things. This one is phosphofructokinase, and it's the one that's responsible for converting fructose 6-phosphate into fructose 1,6-bisphosphate. We also have hormones that are made of protein: insulin, glucagon, growth hormone, thyroxine. And here you can see human growth hormone. Now, obviously, I don't expect you to memorize what you see here. I just want to remind you that they're protein. And so here we see the alpha helix, the secondary structure of this. We see the tertiary and the quaternary structure of these things. And so again, I'm just trying to remind you that most of the time we show you these very schematic representations of proteins in the human body, and in reality, this is what they tend to look like. Then we have neurotransmitters, including glutamine and glycine. Tryptophan gets made into serotonin, which is a very important neurotransmitter. Tyrosine can be made into epinephrine and norepinephrine. Proteins can also act as paracrine agents. Again, these are hormone-like substances. And so histidine is made into histamine. You remember histamine, again, from talking about the immune system and the mast cells. An interesting thing is that around the world, a lot of people eat insects and bugs to get their protein. And so about 10% of protein consumed worldwide is from insects and other bugs. It reminds me of a joke I heard when I was really young. How do you know a happy motorcycle rider? By the number of bug stains on his teeth. At any rate, would you eat an insect or a bug to get protein? Maybe a chocolate-covered ant, or maybe a roasted grasshopper. I had a student who came from the Atlanta area. He told me that in the airport there, they actually had different flavored roasted grasshoppers, including jalapeno flavored. He was supposed to bring some back for the class. He never got around to doing that, but at any rate, there you go. Protein is also very important as a structural component of the human body. It makes up lots of different tissues. Again, you know that collagen is the most abundant protein in the body. You know that collagen supplements don't do you any good because they get digested and they don't get made back into collagen. You might remember from studying muscle last semester that myosin, actin, titin, nebulin are important components of the sarcomere. And then we have plasma proteins. And again, the major plasma protein is albumin. It does a number of things, but one of the things it does is it helps to set that colloid osmotic pressure inside the cardiovascular system, one of those starling forces. And then we also have fibrinogen, which it helps with blood clotting, complement, and antibodies, which both are part of immune function. And here you can see the antibodies that are produced by the plasma cell to go out and try to inactivate and label this bacterium so that it can be gotten rid of. And then another very important protein that we find in blood, it's not a plasma protein because it's inside the red blood cells, is hemoglobin. Again, you can see the secondary and tertiary structure of the alpha chains, and you can also see the secondary and tertiary structure of the beta chains. And then we put all four of them together to get the quaternary structure. The other thing that you can see here, if you look closely, is the heme group in each chain that we have. It's the heme group that will bind the oxygen. Remember oxyhemoglobin dissociation curve? And then proteins are also really, really important components of cellular membranes, both the cell membrane but also plasma membrane of organelles. And they can be receptors, they can be channels, they can be pumps. Down here you see a ligand-gated ion channel. And so as the ligand binds, the channel opens up, sodium comes in, and we get a depolarization, EPSP. But at the same time, a little bit of potassium leaves. Here you see a voltage-gated sodium channel. This is an interesting depiction because they're actually trying to show you some of the protein here that makes it up, as well as the schematic. And then here's another depiction of a ligand-gated ion channel. This one is a nicotinic cholinergic ligand-gated ion channel. Oh, here you can see those gap junctions that are very important in the intercalated discs of the heart, as well as various smooth muscle, small intestine, some places in the liver, other places. Here you can see a calcium pump that is in the membrane of the sarcoplasmic reticulum. And so the calcium is grabbed out here in the cytoplasm and then pumped back into the lumen of the SR. And so again, Lots and lots and lots of functions for protein. Very, very important to you. Well, what are common dietary sources of protein? Most of you know that animal sources provide us with good protein. It's considered complete, and that means, well, it contains all the essential amino acids in a proper proportion, and it has non-essential amino acids to provide a high nitrogen content so that it can make other amino acids as is needed. Plant protein is considered incomplete. The reason it's incomplete is because no one vegetable source contains all essential amino acids in the right proportion. So we have what's referred to as a limiting amino acid. That's the essential or indispensable amino acid, which is found in the smallest amount. And so, for instance, grains and rice are low in lysine. Legumes, including dried peas and beans, lentils, soy, peanuts, they're really, really good sources of protein. They tend to be low in methionine or cysteine. But the point is that if you make a lentil soup and you stick in some peas and some other vegetables, all of a sudden now you have complete protein. And so it's really, really easy to get complete protein from vegetable sources. It's not hard at all. What should your caloric intake of protein be each day? Well, what's recommended is approximately 12% of total calories. And again, the acceptable macronutrient distribution range is fairly large, from 10 to 35% of calories that you take in. And so you can see this, a lot of people would think is way too low, and some people would argue that that's too high on the other end. What we know you need is 0.8 grams per kg of body weight. And we round that off and we just say, 1 gram. 1 gram per kg of body weight. So if you weigh 50 kilograms, you need 50 grams of protein. You weigh 100 kilograms, you need 100 grams of protein. If you want to do it based on pounds, then it's 0.36 grams per pound of body weight. The vast majority of the guys who work out in the Lilly Center get way more than this. They get way more than that. We do know that activity seems to increase your need for protein based on body weight, at least in the short term. There's some data that suggests that after about 14 days, this added need has dropped back down to about 1 gram per kg. And so that's interesting, and we need to look at that a little bit more. But clearly what that means is athletes need to take protein supplements, right? Well, let's look at this guy. This guy is a bodybuilder from back in the 40s and the 50s. And he actually was Mr. USA in 1947. And this was before protein supplements or steroids were available. And so he didn't cheat and he didn't take protein supplements. And yet he looks better than pretty much anybody I've seen in the Lilly Fitness Center in 20 plus years, who all took protein supplements, and some of who took steroids. Here you can see some of his competitors. Here he is again over here. And so this guy actually, Steve Reeve, he was one of the early Superman in some of the early movies. But again, all of these guys competed when there were no protein supplements and there were no anabolic steroids. And they seem to have done pretty well at building muscle mass, don't they? All right, well, let's look at obligatory protein requirements. The obligatory protein requirement is the amount you need to get in your diet each day to equal what is lost. And so that gets back to our concept of nitrogen balance, which we've talked about before. Nitrogen balance means you're taking in your diet, that's the only place you get nitrogen and protein, equal to what you're losing. It's estimated that you lose about 50 to 60 milligrams per kg per day of nitrogen. This diagram is looking at protein, not nitrogen, and so the numbers don't quite match up for you. So if we look at somebody who weighs 100 kilograms, pretty good sized person, 220 pounds, they're going to lose about 5 to 6 grams of nitrogen per day. You lose it in your urine, you lose it in your feces. And so you're constantly losing epithelial cells from your skin surface, and also from the lining of your GI tract from the mouth right on down. And so that is indeed lost in fecal matter. And then you produce mucus, which is made from mucin. That's a protein, and you lose that in your feces as well. Again, as we said earlier, protein is 16% nitrogen, and so 5 to 6 gram loss of nitrogen translates into 33 grams of protein per day that you lose. Okay, and then a safety factor has been added to that to correct for what's referred to as digestibility of proteins, and also to account for individual variability. And so we come up with 1 gram per kg of body weight per day as your nitrogen, as your protein need. So that's what we've got. So let's look at some math here. Oh, numbers. My God, I hope this doesn't freak anybody out. A pound of muscle, we convert a pound to grams, 454 grams. That's what that is, 0.454 kgs. You might recognize that. Of which 70% is water, 22% protein, and 7% lipid. Well, that means that 1 pound of muscle contains 100 grams of protein. How did I get that? 454 grams times 0.22. 100 grams of protein. That's a pound of muscle. So if you wanted to gain 1 pound of muscle per week, which is a little bit on the ambitious side, that would require the intake of 14 grams of protein per day beyond your normal need. Obviously, if you wanted to gain 2 pounds per week, well, you need to double that, 28 grams of protein per day. And so we're going to calculate the protein gain for a 70 kilogram male, a little bit on the light side for a college-age male, given added 22 grams of protein per day due to exercise losses. That's what we're going to add here. So we've got our 70 kg guy times 0.8 grams per kg of body weight. Well, there's 56 grams. Add on the 28 that we have up here, to gain 2 pounds of muscle per week, we're up to 84 grams. Add 22 grams due to exercise losses, and we're up to 106 grams per day. All right, that must be pretty tough to do, right? Obviously, you couldn't do this without taking protein supplements. Well, here, let's look at a possible diet. A couple of eggs, a glass of milk, a couple of slices of toast, and a banana. There you can see the protein content of those guys. A roast beef sandwich with 3 ounces of roast beef. That's like a mouthful for Royce Johnson. 2 slices of whole wheat bread, a cup of mac and cheese. Dinner, baked potato, 1 cup of peas, 8-ounce chicken breast, and 2 cups of milk. Nathan is starving after he eats this. And a snack, 1 teaspoon of peanut butter and 1 bagel. Look at that, 174 grams of protein. Did we hit our goal? The goal was 106 grams. Went well beyond it. Well beyond it, without taking a single protein supplement and without stuffing ourselves. Most of the athletes on DePauw campus, the male athletes, are going to eat more protein than this in a day. Okay, what about the protein need for a typical female? Again, we're looking at somebody who's a little light for a college female athlete. 56 kilogram woman needs 45 grams per day. We're going to add 14 grams because she wants to add a pound of muscle per week. Most women don't want to do that. We're going to add 22 to cover any loss due to exercise. The total for this woman is 81 grams of protein per day that she needs. That's what she has to get. And that's going to support her exercise and her adding muscle mass. Well, 2 cups of milk, 16 grams. 4 ounces of meat, 32 grams. 1 baked potato, 3 grams. Look at that, 51 grams. She's eaten a small meal and she's already almost there. This doesn't count breakfast or lunch or snack. Okay, well, how big is 4 ounces of meat? This is approximately 3 to 4 ounces. And so think of a deck of cards, not very big. Most people, when they have meat, they're going to eat more than what you see right here. And so this number is lowballing or underestimating the protein that they're going to get, if anything. All right, well, what if we look at a woman who is a little bit more typical for a college-age athlete? 70 kg, well, she needs 63 grams, 28 grams because she's really ambitious. She wants to add 2 pounds of muscle per week. And even most of our women athletes don't want to add that much muscle. 22 grams to cover losses due to exercise. And so now we come up with 128 grams per day. That turns out to be 1.8 grams per kg of body weight, which is more than twice our 0.8 grams that we said is needed. So 6 ounces of chicken, we've increased the size of chicken a little bit. Half a cup of peas. Look, there you can see how much a half a cup is. Not very big at all. 2 cups of milk, a slice of bread. And so again, a modest meal. A modest meal. She's at 72 grams. She's more than halfway there. And again, it doesn't include the 2 other meals and the snacks that this woman is going to eat in order to reach that. So you can see. Now, obviously, animal protein is needed to build muscle mass, right? Well, look here. This is an adult male silverback gorilla. This one in particular weighs about 400 pounds. He is a vegetarian. Look at those pecs. What do you think this guy could bench press? I bet he can out bench press anybody in class. Right, Lance? Okay. I don't know this guy. I looked him up. His name is Torrey Washington. He claims that he's a vegan bodybuilder. Not a real big dude. He's only about 5'7", and he's under 200 pounds. This guy, I'm not even sure how to pronounce his name, Babu Mian. He's just under 250 pounds, so he's a bit bigger. Now, I can't guarantee that either of these 2 guys isn't taking steroids, but even so, they're still meeting their protein need through vegetables. And then it turns out that the Tennessee Titans, this guy is a 313-pound defensive end for the Tennessee Titans, and he and a number of his teammates actually were vegetarian for a good chunk of the season. And this guy is also a vegetarian, 313 pounds. Pretty big dude, pretty big dude. So there you go. And so it turns out that no, animal protein is not needed to build lots and lots of muscle mass. Not needed at all. Okay, and then we'll finish up with just a little bit of research that we have looking at some of this stuff. This is interesting. Testosterone is one of our primary anabolic steroids. Resting levels of testosterone were highest when the ratio of carb to protein was 4-to-1. 4 carbs to 1 protein, 60% to 15%. That same year, this is actually Journal of Applied Physiology if you want to look it up, a different researcher found carbohydrate consumption in the first hour after heavy weightlifting decreased protein breakdown, and it resulted in a positive nitrogen balance. Wow, what do you know? Carbohydrate, positive nitrogen balance. It helped to prevent the athlete from having to break down protein as an energy source. That's how it worked. And then another study done in 1999, researcher out at the University of Iowa, he found there was no difference in protein synthesis after resistance training for athletes who ingested 20 grams of protein versus 40 grams of protein. So you need somewhere around 20 grams of protein to support protein synthesis after you do weightlifting. Well, look at this. 3 ounces of tofu, not very much at all. 1.5 cups of mixed vegetables and a cup of brown rice. Well, there's 20 grams of protein right there. Holy crap. And so that brings us to the end of our nutrition videos. Probably next year, the kids are going to have to listen to videos on vitamins and minerals, but you guys, you don't have to.